Warm greetings to everyone listening here. This is Pooja Vijayaraj, and I'm doing my final year in electrical engineering from Sri Muthukumaran Institute of Technology, Chennai, India. So today's talk is basically going to be on solar, and it's primarily focused on inverters. So as I carry you through this presentation, I assume no prerequisites from your side. There's no need for any prior knowledge. Just feel comfortable as I go on with the talk, and in case if you have any doubts, like say any basic question or be it advanced one, just feel free to post the questions and I'll take in questions then and there. So now, before getting into the presentation, let me start off with a little talk on STEM. As you know, right from my school days, I've chosen math and science as my favorite subjects. So it's it's something like it lets you think, and it makes you to solve any situation given to you in a more interactive and more in a creative manner. And the best part is that it actually allows you to already it allows you to connect the already known concepts. So that each and every move which happens in this on this earth, it has a reason behind, and you can actually know how things work. And so that's the best part. It makes you think, and it lets you work in teams and interact and come out with solutions. And that being my reason, I ended up choosing electronics and physics during my pre-university days, and I ended up taking electrical engineering in my college, and I'm currently doing final year. So engineering, as I said, it's on demand. It's a field which is booming right now, and it has such a wide range of professions, and it even allows you to club two or more streams. Like say, if I'm interested in biology, math, and I wanted to club it with engineering, I can come up with biomedical engineering. So it gives you the flexibility. It's not that you're just restricted to one field of study. You can combine streams, you can move from one to another. So that's the best part. You can move across, and there are no fixed boundaries. There are no set walls against which you cannot move or something. And the very thought that the solution which you come up with is going to benefit the society, and it's going to help. It's more for a humanitarian cause. That's enough to give you the boost to take up that engineering profession as a lifetime choice. And I should talk a little about WIE, and I should say that WIE is such an amazing platform. It lets you to organize events, and it lets you to share ideas and network with everyone around, network with other women professionals. So if you're stuck anywhere, it lets you to talk with some other people who have who are already into the field and who are more experienced. They're there to guide you, they're there to mentor you, and you get more industrial contacts. So it's such a amazing opportunity that's actually bestowed on us, and it's up to us to make the best use of it. And we have organized a couple of activities in our student branch. It's SMIT SB-61411, and few of the WIE activities would be, we have organized environmental summits, and we have come up with a lot of workshops, and we have organized a lot of technical seminars, and many more are coming up as well. So so each and every event I've organized, I've faced a fresh set of challenges, and it has actually fine-tuned my skills, and I can carry forward those lessons when I organize next event. So each and every event which I come up, it's like I'm growing. I feel that I'm growing, and I'm more passionate about it, and I'm more energetic, and just thinking about WIE gets me excited. So engineering, though it is a lush field, everyone's talking about it, there is some, sorry, and yeah, as engineering, it's a field, everyone knows that it's on demand, and there are many people who have actually started taking up, but there are some people, there are some preset notions, like, which is, it's actually wrong. Some think that it's only for those who are born nerds, or you need to be geeky to take up engineering courses, or it's restricted only to those people who sport big glasses like me. So it's nothing like that, such notions, they do exist, and some even think that it is like it's only restricted, only to restricted to a bunch of equations, crazy equations, mathematical terms and derivations. So it's that set of thinking, it tells that you're more you're more fixed, or you do not see anything away from the boundary. So when you start looking at engineering on a different light, you'll come to know that you learn things by doing. So there's one common saying that each idea can be visualized and every concept can be implemented. So it's only when you start doing things, like say you learn some two concepts each day, like today, say I learned a concept and I want to learn it, just start doing it. So only when you start doing it, you'll commit some mistakes, and the lessons which you get out of those mistakes is going to carry you forward. Like those are the lessons which going to retain, which is going to retain in our memory for a long time. You're not going to forget it, and that's how we climb the steps slowly, and that gets us more interested about it. So having said that, let's move into the technical presentation. And my presentation, as you know, it's on solar inverters. So before I get into solar inverters, I want to touch upon few basics, because like for people who for whom like solar is a new topic, they shouldn't feel out of place. So let's just a few touch upon photovoltaic systems, and then we'll get into what inverter designs are. So photovoltaics, when I say this word like photovoltaics, photo is light, and you use the light energy, and you tap the light solar energy and convert it into electricity, and that electricity is going to power up the loads. That it can power up residential buildings, or industrial complexes, and any other commercial loads. Yeah, so take any photovoltaic generation system, you're bound to come up with 5 or 6 basic components. It's going to be your solar panels, and then it's going to be your inverters, and then it's going to be a battery which would serve as a backup, and it's going to be a solar tracker, and it's going to be some other accessories like interconnecting wires. So these are the 5 basic points which you can touch on when you say photovoltaic systems. And to start off with solar panels, you can also call it as solar modules. Solar modules, as you know, they are mounted on frames, and they are put on roofs on top of the buildings, or In case of residential apartments, it's going to be on top of your building, and even like many other industries have started, they tap energy from the solar panels for their light loads. And any typical solar panel would consist of 42 to 72 solar cells, and each panel, a typical panel would have a standard voltage rating of 25 to 40 volts, and its power rating would be around 250 watts. All right, so as I said, so each solar panel is going to be a panel. Just consider it as a rectangular piece of frame, and you're having your solar cells connected in it in series or parallel, and each solar cell, and it's connected in parallel to a bypass diode. A diode, you can consider it as a switch, and that diode, it's connected parallel to the solar cell, and but of opposite polarity. Say like your solar cell is connected like plus and minus. Your diode, which you're going to connect it in parallel to the solar cell, you're going to connect it as minus and plus. So during normal operating conditions, normal operating conditions, your solar cell is going to be forward biased. Say it's going to be in operation, it's going to be working, it's going to be in on mode, and your bypass diode, it's going to be negative, it's reverse biased during normal operating conditions, and it wouldn't work. So this forward bias solar cell would do the necessary operation. It would generate electricity, and it send it to the inverters. But during your what do you say, during a short circuit or any other glitches which might happen, your solar cell is going to be reverse biased, that is, it's going to be in off mode, and at the same time your bypass diode, it's going to be in on mode. So your bypass diode, what it does is it will divert the short circuit current, which is going to be in large magnitude, and which is of potential harm to the solar panel. It's going to give way to the current to the external circuit. So it just diverts that high magnitude current, which is a resultant of the short circuit on the panel. So that way these bypass diodes, they prevent a potential hotspot heating. So hotspot heating happens when large magnitude of current flows through the panels, and which is not healthy to it. So you use bypass diodes. So bypass diodes, it's integrated with the solar cells, and it comes with the panels. So that's that ends the topic on solar panels. The next, I'm going to talk about solar charge controllers. Solar charge controllers, the very term is self-explanatory. It regulates the flow of current, so it regulates the flow of power. So what solar charges, when you consider its design, it's connected in between your solar panel and your battery. So it regulates the flow of power to the battery. Battery, as you say, like according to its rating, the power flow should be optimal. It cannot exceed, or it cannot come down a set value, because that's going to make the battery dysfunctional. So what the solar charge controller does is it regulates the flow of current to the battery, so that your battery is not overcharged, or at the same time it does not undergo deep discharge of current. So the solar charge controllers, it also allows you to connect your battery with different types of DC loads. and so it makes your battery function at its normal operating conditions. So that's about the solar charge controllers. And there's going to be solar tracker. Solar tracker is nothing but it's quite a recent technology where your solar panel is going to shift its position according to the according to the position of the sun at any time of day. Say for example at noon, your sun is going to be at overhead, so your solar panel is going to be flat, like it's going to face the sun, so that maximum power can be generated out of your solar modules. And so it's nothing but solar tracker is nothing but it's going to track the movement of the sun, and it will shift its position according to the position of the sun, so that you get optimal power. And the interconnecting wires are like it's the wires which connect the modules, right? Like solar panels, obviously we're not going to have just one solar panel, we're going to have many other panels, and those panels, they're connected either in series or parallel. When you connect say n number of solar panels in series, you call it a string, and when you connect those solar panels in parallel, you call it an array. So it's like series and array. So, and that's those are the standard terms to use when you see how the solar panels are connected. And those interconnecting wires are obviously like made of wires of higher conductivity, so that say copper or silver, so that it's actually able to divert to get the current which the power module solar module generates, and divert it to the loads. So that is the basics of what a photovoltaic generation system is going to be. And nowadays we have a two different set of designs, two different setups of photovoltaic systems. One is grid interconnected solar system, and the other is going to be a stand-alone solar system. A grid interconnected solar system is where you connect the solar panels to the grid, to the utility grid, that is your transmission lines which runs along. So during the light load conditions, when the demand, say suppose I reside in a residential building and I have a solar panel at the top of my building, and during like say suppose like 10 or 11 a.m. when the loads are not reaching at its peak, when the power demand is minimal, you have your power generated out of these solar panels, which is fed directly to the grid. Grid is nothing but an interconnection of electrical networks. So when the demand is minimum, the power is directed to the grid, and when the demand is high, the power generated from the solar panels, it's diverted to the loads. Like say this building is having a solar panel and the demand is high, the power generated from the panels, it's going to reach my building instead of going to the network. And when the demand in this building is low, it's going to be diverted to the grid. And that's an agreement between grid connected photovoltaic systems is generally an agreement with the residential complex who are having solar panels, and the local grid utility company. So, and you'll be paid for the power which you actually produce, and give it to the grid. So that is grid interconnected system. And the next is going to be a stand-alone system. Just a second. And sorry. The next is going to be a stand-alone system. Stand-alone system is like it comes in two types, like with batteries or without batteries. Say, like without batteries, the stand-alone system is going to be directly connected to the grid, the electrical grid, and so such type of solar panels, it's going to generate only during the day. That is only when during the sunlight hours you'll get the power, and during night hours you won't be the solar panel will not be able to generate any power. And that would be so during night hours you cannot use such type of panels. Only during the day, when it can generate power, it will either direct it to the grid or to the building. And the other standalone system is going to be with batteries. So batteries is going to serve as a backup. So when during light load conditions, when the grid can supply the power to the building, the extra power which is going to be generated out of the solar module, it's going to charge your batteries. So such a way, like your batteries are going to get charged during the day, and during the night hours, or when there is a power cut, your battery is going to supply the loads. So that is like without batteries and with batteries. So and it's like in today's scenario, there are almost all grids come with batteries, because it serves as a backup. Say, like if there's a blackout or there's a power cut, and so during emergency situations you need power, you can get power from the batteries. Instead of totally relying on your solar panel, your battery serves as a good backup. And there is going to be something on there's something called MPPT, maximum power point tracking. You have many algorithms on it, like say for example P and O, like perturb and observe algorithm, and you have bang control algorithms. Those they basically, what they do is they make sure that your solar module at any point of the day it generates its maximum power, and it's functioning at its maximum efficiency. So it's basically like it's going to track how the solar how the solar sun position is, and it's going to get the maximum output of the module. And so MPPT and such algorithms, they're usually implemented to get the maximum power, to make it more efficient, and to get the best out of the module. So here so this brings an end to a basic run through over the photovoltaic systems, what are the designs are, and and what the basic components are in a solar plant. So that's basically about the solar plant. And my research is basically, now my research interest is more on solar inverters, and I've made it as my final year project. And solar inverters and its harmonic reductions. So solar inverters is like how how a basic solar inverter is going to be. An inverter is something which is going to convert your it's going to have switches. Yeah, it's basically switches, like there's either IGBT or MOSFET, but usually, like, to get the maximum efficiency, you go for IGBT switches. And solar inverter, it can be single phase or three phase. Like when you go for single phase, you have two legs. Each leg is going to have two switches, and so you have four switches in total. That's going to be a single phase. And your three phase inverters is going to be it's going to have three legs, and each leg is going to have two switches. So that's what a solar inverter, the basic design is going to be that. And as you know, like there are many designs coming up in the market, but the inverter basically, it should have the capability to eliminate the harmonics generated in it. So like the power which you get from the solar panel is going to be DC, and it also comes with distortions in it. Say it's not going to be a complete smooth DC signal, but it's going to have some distortions, some disturbances. It can be due to interference from adjacent telephonic networks, or it can be due to you're getting power in not in a proper sequence, like you have noise added to it. So that's when it's the DC waveform gets distorted. So when you get it in the output, like the output of an inverter is going to be AC. All loads which we use are AC. So when you get it, you don't get a pure smooth AC waveform. It's going to be distorted. So your inverter should have the capability to eliminate those harmonics, those noises. It should eliminate those disturbances. So we have to achieve that, you have to come up with different designs, like not just manipulating the design of the inverter plus some additional some additional accessories added to it, which is going to bring down the total THD. THD is total harmonic distortions, and you have to best design would be an inverter whose THD is going to be less than 0.5%. And so to achieve that, you have to do some manipulations, and the designs I have considered so far, I'm currently analyzing what are the different designs which are actually there in the market. So I have come up with I've come up with different designs and techniques to improve its efficiency and bring down the THD. So it's not basically designs, but also there are like different techniques. You even use microcontrollers, microprocessors, to get the right signal at the output without any distortions. So the first is going to be on multi-level inverters. As I said, like inverters, but with different levels. You have not just a single level inverter. It's going to be, say, 5 level inverters, or 12 level inverters, or it can even reach 25 levels of inverter design. So the more number of levels of inverters, if you keep adding on, the harmonic distortion which is at the output, it's going to come down. So the number of levels and the harmonic content are inversely proportional. So the more number of levels you add up, the less is going to be a harmonic content. That's one, the basic design approach many are following right now. And and as I already said, there are different control algorithms. There's MPPT, that's it's commonly used, and there's another bang control, and many people are even going into fuzzy logic controllers. So all these control algorithms is fed into the microcontroller, and it is the microcontroller which is going to give the pulses to the inverter switches. Like as I said, inverters are basically switches, and you can have single or three phase. So each switch is going to be acted upon by firing pulse. A firing pulse is it's a pulse which is going to switch on the inverter or off the inverter. So it's nothing but a digital pulse which you're giving to each switch. And so these control algorithms, as they are fed into the microcontrollers, they control the firing pulses, the occurrences of the firing pulses to each diode. And by manipulating these firing angles, you're going to get an output which is going to be you're going to get the output which you desire. So apart from the control algorithms, you have different switching techniques as well. Like most prominent one would be PWM. It's pulse width modulation. So what exactly happens in this PWM technique is that you have a reference signal and you have a carrier waveform. So you're just going to compare those waveforms and you're going to come up with an output which is a resultant of which is actually a rectangular waveform. So you're going to compare your a reference signal with the carrier signal, and whatever you get at the output is going to be the signal which you're actually going to send it to the switches. So that's how basically a PWM technique works. And it's not just PWM, there are many other switching techniques which are coming up right now. Others would be sinusoidal PWM, and there are like trapezoidal waveforms and staircase waveforms. And staircase is generally, as the word, it's self-explanatory. You have a number of a series of steps. The signal would consist series of steps. The more the number of the more the number of levels of steps, the less is going to be your harmonics. So, and recently the best technique, it would be chaos based elimination technique. Chaos based elimination is like you have one you have one you get a signal from the inverter, and you feel that you have like, as like harmonics, you have orders in it. You have first order, second order, third order, fourth order, it goes on. You have a number of harmonics, and if you go for a three-phase inverter, your third order harmonic is going to be really less. And so those those harmonics, say suppose like you're getting a signal and it's having say fourth and seventh order harmonics are really high. In chaos based elimination, you give harmonics which are opposite to that of the fourth and seventh harmonics. Say I have fourth and seventh order harmonic, and I'm going to give a harmonic which is opposite to that of that. You know that like opposite harmonics, you're going to cancel each other, so that way it's going to bring down your harmonics. So chaos based elimination is one of the latest one which has come up. And there's another called space vector modulation. And again, space vector modulation, you go in for on different control techniques to bring down the harmonic levels. So besides the your techniques and your PWM techniques, and by varying your switching angle, you can even vary your modulation index. As I said, in PWM there are two waveforms, that is your reference and your carrier. So when you're comparing, you're getting an output waveform. So what you can do is you can modify the amplitude of your reference signal and the carrier signal. So modulation is basically AR by AC, and by modifying those ratios, by changing its levels, you can bring down the harmonics. That's another method. And you also know that these waveforms, when you increase its switching frequency, like the switches which are there in the IGBT, when you switch it on and off and on and off, like when the frequency is going to be high, the output harmonic is going to be really low. So switching frequency and the harmonic content, again, they're inversely proportional, and that's also a technique that's used to bring down the harmonics. And besides from these techniques, you have you can employ filters, like say like smoothing reactors. Their filters are basically what's going to bring down those harmonics to a lower level. And those filters, basically you have active passive filters. it's, it's basic design. If you say filter, you can think of as an inductor and a capacitor, and that's basically what a filter is going to have. And you can have those filters like series. In series, you can have a series filter, and you can have it parallelly and call it shunt filter. Those filters, you can add it to the external circuit as an accessories, you can bring down the harmonic distortion. So the ultimate aim would be to bring down the distortions so that your inverter is more efficient, and such way you can boost the performance of the solar module. So so these are like basically so these I've been analyzing, and I got down to all these designs, and I'm trying to integrate what my prime focus now at present is. I'm trying to add in more features, like say like pick a feature from this and pick a feature from that, and when I combine it, what's going to be my resultant output. So I've come up with different designs, and comparing techniques, and adding filters, and adding another potential components like transformers, and you just see how your output waveform is going to be, and to bring down the harmonic contents. My and as I said, my interest is going to be to bring it down to less than 0.5%, and this is what I'm currently aiming on. And I just hope that I come out with such a design so that this gets out into the market. So so that brings us to the end of this presentation, and I'm done with my talk. And I just want to share this idea with you, like if any of you listening out there, and if you're interested particularly on solar inverters and its design, and you think you can pitch in and add more ideas to it, you can feel free to contact me. You can reach me at pooja.vijayaraj@gmail.com. It's pooja.vijayaraj@gmail.com. You can reach out to me. We can probably share ideas, work on it. Like if you're so very interested in solar, and you want to work on renewable energy sector, we can have a discussion. We can probably start a mail thread and start working on this, so that I just hope that there are like people coming up, and we form a team, and there's always more power to WIE. We can come up with a best design, which is my ultimate goal. And so before I end up this presentation, I would like to thank the organizer of WeChat series, Ms. Kayana Tennant, and also of course Ms. Neeta Patel, who's more seriously into this WeChat, and I just feel blessed to have this chance to talk to you, and it's just such an amazing opportunity to share my project ideas. Whatever I know about solar technology, it's such an amazing opportunity, and hope I made the best use of it. And before I actually leave, I also like to thank my mentors, Mr. Hari Krishnan and Ms. Kamla Tamilvanan, who are the mentors of a student branch, and who actually guide us, and I'm just it wouldn't have been possible without them. So thanks a lot once again. Thanks a lot for listening. And if you have any questions, you can reach out to me, and I'll be very happy to answer it back to you. Thanks a lot again. okay, there are a couple of questions. One is that how did you choose your engineering field? So my, as I said, like my pre-university days were like, I chose science stream. I had physics, chemistry, and biology, and my interest was more on physics. I liked how it worked, and I liked the laws, and and each law had an explanation, it had a reason behind it. So whatever concepts I went through, I got its real meaning. So it's when you start understanding the concepts thoroughly, and you get a clear cut picture in front of you, like why is that law existing and how it's applicable. So when you get the total essence of that subject is when which gets you interested. So I found physics in that case. My physics is one of my favorite subjects out of that, and I thought, why not take up electrical field, because electricals is, again, it involves more of physics laws, and you need a firm foundation in physics. And since I thought I'll pick it up so that I can actually build on those concepts, and make something good out of it. So another question is, what are a few of your motivators? What makes you excited about doing what you do? So this is another question which I have received. So motivation is like, that in particular, and when you're into engineering field, like motivation, it's like every day there is something which motivates you, because even if you just go outside and see around, you have everything is marvel, and it's a result of what people have worked in engineering, like be it the automobiles, or be it the work in the lighting in malls which you find, and be it anything, and even the software, like everything which you see, the smartphones, they're all the acts of engineering. So when you feel all that, when you see things, when you see common things around you in a different perspective, you see that all those are the results of what people have done in engineering, and how people think, and how each day is like an advancement in technology. So when you see all that, you feel motivated. Okay, why not? Like, even we should start learning what we what's around. We should build a system which is better than which is existing right now, and the outcome is going to be just amazing. You feel such enthu that you have come up with a design, or it's not necessary that you come up with something new. It's it is good, like if you come up with something new, but if you even if you improve a small feature in it, and you get a new design out of it, it's going to get you excited, because your name is going to be at the end. It's because okay, so and so person has come up with a design, and it gets you all invigorated. So that gets you excited. It's basically like engineering, as I always say, it's more about thinking. It's how you think and how you come up with designs. So that's basically what I say engineering is. And another question is, what is your involvement in IEEE Women in Engineering? So I joined WIE during my second year of study in engineering, and when I just started off with WIE activities, I didn't know much about it. I didn't know how it worked. But as I actually started learning it from my seniors, they actually shed light on how you take up WIE to organize events. Okay, it's not just organizing events, you can even take it in in a different note, like you have many activities which are you can participate in. You can in the tag name of WIE, you can venture out, you can meet new people, you can get into organizations and have a talk with them, and you know you can probably get their help, their advice, and what they have experienced, their challenges. So you get all such good advice, and before you actually venture out into the industry, you get all the field knowledge, which is more important, rather than your textbooks. Yeah, okay, your textbooks again important, even though they don't sound that interesting. Apart from it, it's what you say, WI is an add-on, which is going to boost your performance. It sets you out from the crowd, so it makes you look so smart. So that's what we is about. And so basically, WI I'm involved in both student branch and Madras section. At the student branch, as I say, like, I organize events and bring down people from industries to a college, and have allowed them to meet the students, and so that we bridge a gap. And recently we have even come up with ideas to have internship recruitments. So there are many small and medium scale enterprises out there, and they would be interested to have people. So small and medium scale industries, they are like usually startups, you can say. They're just into industries, they're just climbing. So when you get students into those startups, it's going to make them learn more, because I say this because startups, they don't have any hierarchy, like as in a corporate organization in a big company. You have certain hierarchy, like if you want to reach the director of the company, you need to move through each and every single person, so that you reach the you reach a director. But when in case of a startup, you have everyone working on everything, like be it the management side of it, or be it the development side of it. You have a mix of all. So that's what that's what motivated me to have internship recruitment drives in our college. And we are planning to have all these in 1 or 2 months. And we are even planning to have an expo where the industries would display their products and the technologies which they use. They'll have a short presentation and few interactions with the students. So so those are the plans, and those are my involvement in IEEE WIE. And at the section level, I basically do reporting, like whatever events which happens in student branches across Chennai, across Tamil Nadu. I get those reports and edit it, and I'll ensure that they are posted, they are actually published in newsletters. And another question is, how do you see success and failure? Okay, all right. This is another question which I got. So success, okay, and this okay, success is like, there's nothing called failure as such, because as I already said, when you commit mistakes, you're going to learn, you're going to get great lessons out of it. Suffering are the great tutors. When you actually suffer, is like when you learn great lessons. You learn those lessons, and you're never going to forget it, because you experience it. And when you experience it, it's going to be like, you're not going to forget it. It's that memory is not going to fade away, and it's going to stay on with you. So that lessons, you can carry it forward. So at the next level, at the next stage of implementation, when I apply the other ways of doing a particular design. I know, like, you know the ways which do not work, and you come up with new ways, so it actually gets you, you know, thinking in a more broader sense. It's going to shatter your limits. So I don't see anything like failure. It's just success always, no matter what happens. And another question is sorry. Another question is, does the efficiency of the cell change when you connect the solar cell in series or parallel? Yes, it does. Like, it depends on what wattage you want. Like, say, let's get in the basics. I hope you know about you know about the voltage law and the current law. Like, when you're going to plug in circuit elements in series, your voltage drops are going to get added up. Say, like, you have 3 resistors, and you're going to connect it in series, like, say, R1, R2, R3. Like, they are the resistors, and your resultant voltage, that is the total voltage which you get, is going to be the sum of all the voltage drops across R1, R2, and R3. So when you want when you want to improve the voltage capability, you connect it in series, so that your resultant voltage is actually boosted up. And say, if you want more of enhanced current capability, you connect them in parallel. So when you connect circuit elements in parallel, the resultant current is going to be the sum of the currents in each of the branch. Say, suppose you have 3 resistors which are connected in parallel, your current level is going to be boosted up, as because the current in each branch is going to get added up. So it depends on what you want. So that's how you change the you configure the design according to your requirements. Another question is, what is the best advice you have ever received? So advice is like, we know that we come up with like, there are so many people. It's so easy to give advices, but it's a hard step when you start following that advice. So the best advice I would say is to work smart rather than do hard work. So that's because I usually stick to hard work, and it was recently only after I got into like my pre-final year, that I started to follow that advice. Because hard work, it deals a lot of patience and arduous tasks you need to perform, and hard work, so that would actually bring down your energy levels. You won't be it's very hard to make you feel motivated, or you would start losing interest. And so I'm not saying that you shouldn't work hard, that is important, but unnecessary work is not usually it's not advisable, because it's you'll start losing interest, because we are here we are ultimately we're humans. We cannot take in more, we cannot take in more burden. So what I would say is, like, you can take in some easier ways to get things fast. It's not, I mean, this sort of what do you say, I'm not advising you to take shortcuts always, but at some moments when you feel that probably you should opt for an way which fetches your results faster, so that your ultimate goal is reached faster. So in that case, you can probably take such routes. Okay, let me give an example, so that I'm scared, like, if you get that advice wrong. Say, for example, if I if I take to if I want to study a piece of concept, and I start referring huge volumes and books, and which actually drain down my energy and pull me down. So instead of doing that, you can probably look into a video of it online, so that when you watch it, when you can visualize it, you can actually get to learn those concepts faster. You can take up many online courses. There are so many more courses coming up online. You can take those courses and start learning, instead of sticking to the traditional way of learning from books. So if you're tired of it, you can probably think of a new way of learning things faster. So this sort of this way of learning, this sort of divergence is advisable and it's very healthy. So that's the best advice I've received till now. So I guess I'm done with all the questions. So I hope you had a great time listening to me, and I would strongly advise to reach me if you have any doubts, or if you want to work with me in doing this project, or it can be for anything. I'm always open to any comments or any sort of networking. So hope to see you all soon. Thanks a lot for listening. Bye.